Good afternoon, ladies and gentlemen. My name is Kenichi Kuma, and I'm a senior program advisor to Climate Core project. And in fact, in 2019, I had retired from Director General of Meteorological Research Institute at JMA. And after that, Professor Nakamura and Mr. Hasegawa, who is Director General at the time, who is sitting over there, jointly starts a joint research agreement between JMA and University of Tokyo in 2021. And this is a project supported by JST, Japan Science and Technology Agency. And in fact, the project leader is Professor Nakamura, and sub-leader is Abe-san, so WNI Weather News. So this is kind of government and academia and private sectors. This is a joint project. Okay, so let's go to the history. Because this year is 150th anniversary of meteorological service in Japan. And at the time, the observation site in Tokyo is over there. And there is observation. And we need to collect the data. So we need to wired or wireless communication. And we try to draw the weather map like this. And next, this is a map discussion for forecast and like this, and weather forecast and warning to public. So this is a traditional forecast. Forecasters' experience for weather pattern change learned from the past weather map might help forecasters to draw their prognostic map, weather map tomorrow, which is very similar to machine learning, in fact. Okay, so next, the numerical weather prediction. In fact, I have a background in numerical weather prediction. And first, the vagueness. If we know the initial condition and we know the governing law, so that we can predict the weather, he mentioned. And next, Richardson challenge to solve time evolution equation in discrete form like this by hand, not a computer. At the time, there was no computer. So he tried to calculate like this discrete way, but he failed. Maybe all of you know. And this is an equation, dynamical process and the physical process. I will talk about it later, but the way is that the time derivative is given by this kind of equation. So that is calculated every time step in the computer. Okay, so you need the initial condition. So initial conditions are the observation itself is a point observation. So we need a grid data. So we need to transform from a point to the grid data. That is a kind of important thing in NLP to create the initial condition for computer. And for that way, in that way, that first guess, which is given by the past prediction, then this is a first guess, and combine with observation data and make analysis. And so next prediction starts. Like that way, the initial conditions are created. And for the analysis scheme, one of the sophisticated analysis scheme is 4D variation analysis like this. Find the optimum solution using the observation data under the constraint of governing equations. So that is a very sophisticated one. Okay, and very expensive one. We need a lot of iterations. And we need a high performance computer. So the Japanese computer starts 1959 for NLP, and now we are now in the 11th generation, and that computing power is 4 trillion times faster than the first generation machine. And thanks to the development of the performance of supercomputer, the error grow 500 hectopascal height error becomes smaller recently. And in early 1990s, the 24-hour forecast error is about 20 meters. And now the 72-hour forecast error is about 20 meters. So very remarkable improvement in the enthalpy, and same as the tropical cyclone trough forecast. And next, this is reanalysis. Reanalysis uses the same procedure of the enthalpy, but the only difference is we use the past observation data like this. So we can use the 10 years ago data, then we can create the 10 years ago analysis and the 10 years ago forecast. And this is JERA thank you, which is a global reanalysis paper by GMA. And the operational forecast, the error becomes drastically decreased in the last 10 years because of the development of enthalpy. But for the reanalysis purpose, this is it's not good for the uniform quality. So if you use the same system for the past historical analysis, then we can get the relatively uniform quality of the data. So it is similar to ERA 5. So the past observation data, the analysis is a gridded data, so easier to use compared with the observation data, and combining with the observation with the model output. So much better than the, much closer to the real atmosphere compared to the simulation data, and use the same system, so more consistent quality compared to the operational enthalpy analysis. I don't go in detail because this is Google's DeepMind's results. But not only Google, but NVIDIA and Huawei, Microsoft, FANG, Alibaba, they also shown the performance of AI machine learning-based prediction. And this is ECMWF operational AIFS, and the root mean square is better. And in particular, tropics is much better than compared to the extratropics. And activities, it's a kind of amplitude of the weather systems. And the problem is that the AI model has a weaker activities. I'm not sure the recent Google's AI model may overcome that kind of issue. But anyway. And this is a tropical cyclone forecast at the MRI GMA applied Huawei FANG weather forecast trained ERA 5. So typhoon track forecast is better, but intense forecast was bad. But maybe it might be overcome by Google, I guess. But I will explain our approach for this kind of issue later on. So this is a traditional weather map, and every 6 hours. So the forecasts are learned from this kind of change, and the forecasts are carried out. And okay, but the forecast in the early 20th centuries, we only have surface observation. So at that time, only surface map. But later on, we have a radio zone there, and we have a upper level. But it's difficult for forecasters to see all levels for several decades. It's very, very difficult. But the AI, machine learning, can do it. That is one of the reasons why AI forecast is so successful. AI forecast is trained by several decades 4D reanalysis data. That's huge data which human cannot realize. And enthalpy and AI forecast, and we have a dynamical process and the physical process in the enthalpy. And in particular, the physical process, it's very difficult. There is a control and feedback between grid space and subgrid scale. There are a lot of unknown microprocess and parameters. And in the tropics, the role of physical process is more important than the dynamical process. And so that's why enthalpy performance in the AI forecast performs better in tropics, because the enthalpy may not work well in the tropics because of the difficulty in the physical process. And this is a post-processing, which is already mentioned by the National Meteorological Service in Southeast Asia. The guidance which has been developed since the beginning of enthalpy era, it's kind of AI machine learning technology because in the historical database, the entropy GPV and observations, we calculate the statistical relationship. Then we provide we translate from the entropy products to the user-oriented or bias-corrected data like this. So even if we don't have a good we don't have, this is GSM, so the resolution is not good. So we cannot treat the detail of the orography. But so the GSM GPV is not good near the mountain area. But observation knows the orography. So the guidance corrects the GPV using the statistical relationship. So that is a very important post-processing process. Scheme. So reduce systematic errors in entropy output, such as temperature and wind, arising from the poor horizontal resolution, and derive quantitative values not directly calculating entropy models, such as probability of thunderstorm and weather categories, and even consumer demands. For example, how much ice cream will be sold today or not, which are sensitive to the weather. Okay. And guidance for the extreme event requires a long-term database because extreme events does not occur so frequently. So the cases for extreme weather is very, very rare. So we need a long term for 10 years or 20 years. But as I mentioned, that in the operational forecast, we have a very different quality in the long area. So with using the analysis, we have more uniform quality data throughout the long period, which is suitable for getting the extreme events properly. And for end users, we need downscaling because everybody wants to know the weather above the head. So the traditional way is that this one, global model, and lateral boundary condition, the regional 4DDA, and guidance, and go to the end users. But there are many other alternatives, such as statistical downscaling, and downscaling by machine learning, diffusion model, or convolution CNN, and guidance, then go to the end user. And the other approach is regional machine learning prediction and guidance, and then go to the end user requirement. So that kind of there are several kinds of approach for the downscaling. So this is NVIDIA's paper saying they are good at downscaling issues, and there are several important points written here. That adding coherence and kilometer scale prediction and data assimilation capability. That is a future challenge. And the downscaling at different geographic locations from Indonesia or Thailand or Vietnam or various places. So, but here again, the reliable kilometer scale weather data is the issue. And third one is downscaling future climate prediction. It is already mentioned in the Thailand's climate research, and this is also very important. And synthesizing sub-kilometer sensor observations. So observations are very, very important. So, so observation data and how to include the information of observation to the downscale fields. These are very key issues for, I think. We are doing the regional reanalysis in Japan. One is RRJ-Comp, right-hand side, and the left-hand side is RRJ-Climate, our project. And the right-hand side is using the only conventional observation. And the left-hand side, this is a very sophisticated, it's very close to the operational mesoscale entropy system, and using 4D bar, and use most operational, same as the operational data such as satellite data and the radar data and so on, and also utilizing the reprocessed data. And this one, RRJ-Comp performs for from 1950s because only conventional data, so we can get uniform quality for long range. But for the large climate core, for long term, we don't create the uniform quality. So we specified a period from only 21st century. And so the large computer is suitable for long-term climate change detection. The method can be applied to developing countries because this is a very simple analysis system. And the left-hand side is observation quality of product is the same as the current operational GMA model, and most observed information are reflected. So this is a more sophisticated one. And the crime core and the JR3Q comparison. This is Typhoon Hagibis in 2019. The left-hand side is precipitation, QPE, observed precipitation, and the middle one is a 5-kilometer mesh rainfall, and the right-hand side is a 40-kilometer JR3Q. So the 5-kilometer reanalysis produce very, very precise structure of the rainfall system. And this is a wintertime convergence zone in the Japan Sea. And again, the JR3Q cannot produce a detailed structure, but the RJ climate core produce a detailed structure very similar to Himawari IR data. And the uniform quality for long term is also obtained compared to operational model. RJ climate core has a uniform root mean square error and bias like this. In fact, MSM history, there are a lot of improvement during the last 20 or 30 years. Okay. And one more important is that today there are a lot of discussion on precipitation. So we need to get the good precipitation data. So our project to produce reprocessed QPE data as well as regional reanalysis data. That is very important. And in Japan, we have a radar and a rain gauge combined precipitation analysis with 1 kilometer. That is very, very important for disaster mitigation. And but in fact, going back to the 1990s, then resolution was 5 kilometer, then 2.5 kilometer, then finally 2006 it becomes 1 kilometer. So we try to reprocess with 1 kilometer resolution. So that is one of our project. And before doing that, we first improved the analysis method itself. And with the collaboration with the Japanese Space Agency, JAXA, we have improved QPE over the ocean by validating the satellite information. And also through the collaboration with a railway company, JR East. Today there is a participant here. We have improved the QPE over the land by validating with JR East rain gauge data, which is not used in the, this analysis data. So that is very good, important validation data. And this is an example of how the 5 kilometer and 1 kilometer mesh rainfall analysis is different. Right-hand side of 5 kilometer, and the left-hand side is 1 kilometer mesh rainfall data. So to which for the same phenomena, very, very different. And the 1 kilometer produce a better detailed structure of precipitation system. So finally, we hope weather climate service will be remarkably improved both in forecastability and path to the end users through the development of AI and machine learning. And my message, one of my important messages is don't forget the observation, because observation will become more and more important. Thank you very much.